Bismillahirrahmanirrahim. Guys, I hope that you are well in this unprecedented time of COVID-19. In today's lecture, we will talk about resistors in parallel and series combination. So, as was the case with capacitors in our earlier lectures, the resistors are found in various combinations. In order to analyze some electric circuit, so it is very important to calculate the equivalent resistance of the resistors in combination. So in this lecture we will discuss resistors in series and parallel combination, and in later on we will calculate the equivalent resistance of the resistors. Those have series and parallel combination. Now first let us talk about the resistors in parallel combination. So first start with a simple combination. We have two resistors, those are in parallel combination. So we have two elements which has a resistance R1. This element has a resistance R1 and the second element has a resistance R2. So A and B are the terminal. So recall the parallel combination. So by definition, in parallel combination, these two elements are the resistor R1 and resistor R2 have same voltage. I mean the voltage across R1 and the voltage across R2 is same. If I connect the terminal A and B with the battery having a voltage the potential difference del V, then the potential difference across R would be del V, and similarly the potential difference across R2 would be the del V. Now by connecting this terminal with the battery, if I connect this terminal A with the positive terminal of battery, then the current will flow through this circuit, and what will happen? The flow of charge, the potential will remain same across R1 and R2. However, the flow of charge will divide. I mean the current through R1 would be I1 and current through R2 would be I2. Now using the Ohm law, we know that I1 would be equal to, as you know, that V is equal to IR. So this would be equal to del V, which is the potential difference across R1 over the resistance of this element, which is R1. I will call this equation 1. Similarly, the current I2 flow through R2, so which is equal to del V. V is the potential difference over R2. This is equation 2. You can see here the total current is I, which divide into two parts, I1 and I2. So I can say that the total current, uh, okay, the total current which is I, this is divided into I1 and I2. Moreover, the total current through this circuit, uh, which is I, which I can write as I is equal to, which is the potential difference across the terminal A and B, divided by R equivalent, which is the equivalent resistance of this circuit. Now I will plug in equation 1, equation 2 and equation 3 in equation 4. So after this I will get del V over R equivalent, which is equal to del V over R1 plus del V over R2. Now by simplifying this equation I will get, okay, this will cancel with this, so eventually I will get by adding the reciprocal of these resistances which are in parallel combination, so I will get the reciprocal of the equivalent resistance here. So you can see in this equation. Now again I can modify this equation, which is 1 over R equivalent. I will take LCM of R1 and R2. Now again taking the reciprocal of this equation, R equivalent is equal to R1 into R2 divided by R1 plus R2. So in parallel combination, to find the equivalent resistance, what we do, we will take the reciprocal of each resistance, then we'll take the sum of the reciprocal of each resistance which is in parallel combination, then we'll take another reciprocal that will give you the equivalent resistance of that circuit, I mean wherein the resistors are in parallel combination. So this is the equivalent resistance in case we have two resistors in parallel combination. Now let us extend our discussion to the resistor. We have n resistors in parallel combination, so I will expand this circuit as, and this one is Rn. So I can expand this equation for n resistors. So in case of n resistance, 1 over R equivalent would be equal to 1 over R1 plus 1 over R2, so on, plus 1 over Rn. I can write this equation in the form of summation. So 1 over R equivalent is equal to summation 1 to, okay, this is n is from 1 to capital N, and so in this way I can add up the reciprocal of each resistor in parallel combination, and then again I will take the reciprocal of the sum of the reciprocal of each resistor, then I will get the equivalent resistance. Now okay, one thing you can see in this equation, that when if the resistance is high, the value of resistance R1 is larger, then the current flow will be lower. So if here you can see the flow of current through the resistor depend upon its resistance. So greater the resistance, lesser will be the current. So this is the reciprocal. I mean, resistance is the reciprocal of the flow of current through that element. So here, if suppose we have R2 is lesser than R1, in this case the I2 would be larger. Next, let us talk about resistors in series combination. Now, recall the definition of series combination. In series combination, the flow of current through each element is same, but the voltage across each element or each resistor would be different. Suppose let us take a simple example. We have two resistors R1 and R2. This is R1, this is R2. And if we connect the terminal A and B with the battery, having voltage difference or the potential difference, which is V. So the voltage across A and B is del V, and the voltage across R1 and R2 would be different by definition of the series combination. So the current through R1 and R2 would be the same, that would be I. However, if the voltage is del V across the terminal and A and B, it will divide. Suppose the voltage across R1 is del V1 and the voltage across R2 is del V2. So some voltage will drop across R1 and some will drop across R2. Now again, by Ohm law, del V1 would be equal to I into R1. The current will remain same through R1 and R2, and del V2 is equal to I into R2. So this is equation 1, this is equation 2, and taking into account terminal A and B, this whole circuit has equivalent resistance, which is R equivalent, and current through this circuit is I, and the potential across or the voltage difference across A and B, which is del V. So I can write this equation 3. Now you can see here del V1 is the voltage across R1, del V2 is the voltage across R2. So the total voltage divide into two parts. So the total voltage del V is the sum of del V1 plus and del V2. Now I will plug in equation 1, equation 2 and equation 3 in this equation 4. So I will get so I can take a current which is common. So by simplifying this equation, the equivalent resistance is equal to R1 plus R2. So here we can conclude that in case of series combination, The equivalent resistance is the sum of individual resistor in that circuit. So this is the equivalent resistance, which is the sum of the resistor R1 and R2 in series combination. Now let us expand this discussion for n resistor. So suppose we have n resistor in series combination. In this case, R1, R2, so on. This is Rn. So we can modify this equation as plus so on plus Lpn. Again, this equation will be modified plus so on plus R n. Eventually, the R equivalent would be the sum of the all resistances of the all resistor in series. So I can use a summation here, and from 1 to n. Further, by analyzing, so this is the equivalent resistance in case of n resistor in series combination. Okay, now if we analyze equation 1 and equation 2, we can see here if R1 is greater, then the potential across this resistor will be more than this resistor. So it's okay. Now let us solve some a few examples related to series parallel combination. So we have 3 resistors. R1, R2, these are in parallel combination. We have another resistor which is R3. Now we have to find the equivalent resistance across the terminal A and B. And we have given R1 which is equal to 4.6 ohm, R1 is 4.6 ohm, R2 is 3.5 ohm. Yes. Okay. Now you can see here R1 and R2 are in parallel combination. So in case of parallel combination, their equivalent resistance would be, I will say this R12, which would be equal to R1, R2 divided by R1 plus R2. So R1 is 4.6 ohm, R2 is 3.5. I will divide this 4.6 ohm plus 3.5. So eventually I will get the result is 2 ohm across. So the equivalent resistance of R1 and R2 is 2 ohm. Now we can see R12 and R3 are in series combination, and R3 is equal to, so in series we add up the resistance. So the R equivalent would be R123 would be in this case R12 plus R3, and R12 is equal to 2 ohm, R3 is 2.8 ohm. So the total resistance would be 4.8 ohm. So we can say that resistance across, so the equivalent resistance of this circuit is 4.8 ohm. Now let us talk another example. Let us discuss another example. So we have resistor in series and parallel combination. This is R1, sorry, this is R, this is R. So here is the circuit, and we have to find the equivalent resistance across A and B. So here you can see these two resistors are in parallel combination. These two are in parallel combination. These two are in parallel combination. These two are in parallel combination also. These are in parallel combination. So first solve these resistors in parallel combination. So after solving this, so here R and R are in parallel combination. So this would be equal to, sorry, R plus R square divided by 2R. This is R by 2. So I can reduce this circuit as this is R by 2 by solving this. This is R by 2. This is R by 2. This is R. Also, this is R by 2. This is R by 2. Now in this circuit you can see these three resistors, these are in parallel combination. So sorry, these are in series combination. So in series combination the resistance will add up. So next we will get R by 2